All right, so my clock shows that it's 10 o'clock. So I think we'll get started, and then, if more people filter in, then, um, that's fine. But yeah, so the intent of this talk is to give a little summary and a little information on how to schedule resources optimally on the on our systems, so on Cheyenne and on Casper. My name is Brian Vanderwend. I'm in CISL's Consulting Services Group, so we're the folks that answer the help tickets and install a lot of the software on the system, on the systems that you use. So we deal with a lot of these tickets where somebody's running an application and in a batch job or an interactive job, and there's a bit of a question as to why performance is lacking, or why the job failed, or why the job won't schedule. And a lot of times that comes down to the way that the resources have been scheduled in the job. So let me do a summary of the schedulable resources that we have on our systems. And this should be information that's familiar to most people, but I just want to make sure we're all on the same page. So on Cheyenne, Cheyenne is a very homogeneous system in terms of the resources available. So there are only CPU nodes. Those CPU nodes, those standard nodes, have 36 physical cores that you can assign tasks to. Hyperthreading is possible, so simultaneous multi-threading. And if you use that, and if your code uses that effectively, then you can use up to 72 execution threads, each sharing a physical core. A lot of times we don't recommend doing that because the performance gains are small and the performance hit can be large for certain workflows, but that is an option that's available. And the regular nodes on Cheyenne, they have about 45 gigabytes of usable memory. If you just submit a job without any requirements, those are the nodes that you'll land on, and that's the memory that you'll have available, because there's about 15 to 20 gigabytes of memory that's used by various system tasks, like the operating system and the file system. We do have a selection of large memory nodes as well, and you may have scheduled jobs on these using the 109 gigabyte resource tag, which I'll review in a little bit later. But those have double the usable memory. And you can, of course, schedule jobs on exclusive or shared queues. So you either have exclusive access to the nodes, or you share those nodes with other users. And as you should be familiar, PBS Pro is the scheduling interface to run jobs on Cheyenne. Now on Casper, things are a bit more complicated, and this is where the resource requests become more interesting, I suppose, at the moment. So on Casper, we have CPU only nodes, and we have nodes that have CPUs and GPUs. And those GPUs come in the flavors right now of either GP100 GPUs, which are kind of, they're slower, less capable GPUs, but they're perfectly fine for a lot of things like rendering tasks and also running remote desktops. And you can run low resource machine learning codes on those as well. The real workhorse GPUs are the V100 NVIDIA GPUs. These are the powerful general purpose computing GPUs. And we have a growing number of those on the Casper system. We're really hoping that people use those for development and testing of codes, and really exploring the waters as GPUs become more important in the future of scientific computing. In terms of the CPUs, again, 36 physical cores, tasks with 72 simultaneous multi-threads, hyperthreads with Intel's terminology. The node memory on these Casper nodes can go up to about 1,100 gigabytes, so significantly more amount of memory than on the Cheyenne nodes, though not all of the nodes have that much memory. So that's something to consider, is if you ask for a lot of memory, then you're going to restrict the pool of nodes that you can run your jobs on. And the V100 GPUs have 32 gigabytes of video memory for each GPU. So that can be a limiting factor. And I've seen a few users who have a very big problem size on a machine learning task, a large batch size, and it fits on the node, so they can run it in a CPU context, but it actually doesn't. The batch size doesn't fit on the GPU memory. So unless they're doing some sort of distributed algorithm, their problem size doesn't fit, and that gets a little tricky. And there are schedulable resources on these Casper nodes as well. It's kind of silly. It's not a consumable resource, but some nodes have X11 support for remote windows. And there are different CPU types on the nodes as well. Some of the older, or most of the older nodes have Skylake, Intel Skylake CPUs, and the newer ones that we're installing have Cascade Lake CPUs. These aren't very different, but if you have different CPU architectures, you have to be a little bit cognizant of that when you're compiling codes, because they might run on certain nodes and not on others if you're not careful. And as you probably know, if you've run any jobs on Casper, that uses the Slurm scheduler. But I have those dots there because, as you may have seen in the daily bulletin just this week, Casper is going to be transitioned to PBS Pro in 2021. The exact timing of that is a little bit in flux. We're trying to make this transition clean and as painless as possible for users. And really the intent is to unify the scheduling interface that you guys have to deal with, so that you don't have to do this context switching in your head between PBS and Slurm and have to get used to the eccentricities of each scheduler. So everything that we're running will be on PBS Pro at some point in 2021, and hopefully that'll make things easier. That, of course, means that some of the stuff I talk about today will change at that time. So I suspect that we'll give this talk again at some point after this transition and kind of update the things that you need to think about. So why focus on the resource requests? Why put time into optimizing your resource requests? Well, good resource requests can do things like enable you to use less core hours on your allocation. So that is especially important if you're running jobs that have a heavy allocation footprint. You can increase your job priority, and higher job priority means that you have lower queue wait times, so you can get more jobs through the queue more quickly with good resource requests. And sometimes you can improve your application performance as well. So then your jobs, these all kind of feed into each other, right? So if your application is performing better, your jobs are going to take less wall time as well, and the less wall time you use, the higher your priority. So these all feed back on each other. Now, conversely, bad resource requests obviously don't do those things I just mentioned, but they can also cause you to reach an out-of-memory condition on both machines. But on Casper, this is a little more insidious, because on Casper, if you run out of RAM, your application won't fail, which is good, but it will write data to a NVMe swap space. So this is like a solid state disk that's used as a overflow if you run out of RAM, and that runs significantly slower than when you're accessing data on RAM. So that can lead to very slow application performance and in a bit of a not obvious way if you're not looking out for it. And it can, of course, cause submit and runtime failures. So, those we always want to avoid. And in rare cases, and we try to make this as rare as possible, it can even crash nodes, in which case, the node reboots and it comes back online. But especially on Casper or on the interactive nodes on Cheyenne, that's problematic, because if you do manage to crash a node, then everybody else who's on that node is not happy. So we want to avoid that as much as possible. Okay, so what are the things that I'm thinking about when I talk about resource requests in, say, an MPI batch job on Cheyenne? This is kind of the simpler case here. So here's a pretty simple batch script that I've written to do a resource request and then run an MPI application. Now there is a wrinkle that I have here. So PBS has a fairly nice syntax for requesting heterogeneous resource select statements. So, in PBS parlance, the select statement is what you use to really define your various chunks of resources. They call them vnodes. And in this case, what I'm considering is that my application has and this is a random application that I'm not naming. It does all of its I/O on the root node, on the primary node. And therefore, that primary node has much higher memory requests or memory needs than all of the secondary nodes that are doing computation but not doing I/O. So in this case, I can optimize that by saying I want one node, and this will be the first one, that has the high memory availability, the 109 gigabytes, and the other 4 nodes that I need, so I have 5 in total, I'm going to not have that requirement, so they can run on either the regular nodes or the high memory nodes. That either way is fine, whatever is available. And by doing that, instead of requesting 5 high memory nodes, my job will probably get through the queue more quickly. And it also is kind of being a good computing citizen, because then those high memory nodes are available for the users who really need them and the applications that really need them. The other thing I'm doing here is I'm asking for less MPI processes and less CPU tasks on this high memory requirement node than on the other nodes, and that also lowers my memory footprint, because oftentimes MPI applications will use more memory the more tasks you run on a node. So that's another way to eke out more memory if this amount is even not sufficient. So that's one thing I'm doing. I'm expecting the application of higher memory requirements on the head node. The other thing that is not explicitly a resource, but we always recommend doing it, is to set your temporary directory to somewhere in your scratch space is the logical location. And then you want to make sure that that directory exists, because if the directory doesn't exist and it tries to write temp files there, the job will fail. But the reason that we recommend doing that is because there's a /temp space on the compute nodes on Cheyenne, and that space is very small. It's about 150 megabytes. So if your application is writing a lot of temporary files, it's pretty easy actually to exhaust that space, in which case, again, if your application isn't doing good cleanup and frequent cleanup, that can cause things to fail. Some systems have larger temp spaces on them, but we keep it small because that space is it's actually using a fast storage, but it has a small footprint. So better to keep these on scratch. And then finally, I'm storing, this is not really a resource request, but this is information for me in the future. I like to run qstat-f with the job ID at the end of the job, and that gives me a little bit of information that's stored in the future in the job logs. So that'll include the CPU and the memory utilization. I like to put that in there because that qstat-f, which is the full output, that is purged from the PBS database after 1 day. So if you try to look at that, if you try to query that, say 2 days later when you're curious about it, you won't be able to find it there. Something else to consider is the job output and error log placement in PBS Pro. And this is a little interesting. PBS does it differently than some other schedulers. So the application, the output and the error log messages are written to log files during runtime. And you can combine those streams into a single log file with the join option if you want. I like to do that, but that's a configurable behavior. But there are 3 possible storage behaviors depending on how you configure your batch job. So the default behavior, which is the way that we documented for a long time, is that the logs are written to the temp space, that temp space that I talked about before, during runtime, and then when the job completes, they are moved to the job directory that you submitted from on Glade. So if you just use, say, here I'm joining my output and error streams, but I'm not specifying anything else about the logs, that's how it'll work. And again, the problem there is we've seen some applications, especially in debug mode, that write just a ton of output to the logs, and that can be useful output, things like timing, things like where you are in the call stack, what functions you're running. But if you exhaust that space, then your job will fail, and it'll fail in a way that you don't even get logs. because those logs just stay on the execution node. So it can be really hard to debug what's going on, and actually the absence of logs is the main tell for that you're outputting too much data to the logs. You can specify a -KOE. This is a second behavior. This one I don't think it's used by many people, but it's interesting. And just to be aware of, in this mode, the logs are written to the user's home directory. It's written to your home directory during runtime, so you see it as the job is running live. But they stay there after the job completion, so it doesn't move those files to the job directory, which can make them easier or harder to find depending on the way you think about it. But I think that's something that goes against your typical expectation. And another important thing to note is that PBS won't respect the -J, the -O, and the -E options when you use this mode. So I can't join the output and error streams, and I can't name those files. What they'll get named actually the name of the job and then the job ID. So that's really not very configurable. And finally, the way that we've recommended, at least for the past year, is to use this -KOED. So this is the same as this, but there's a D at the end. And here the logs are written directly to the job directory on Glade during runtime. And this still actually supports joining the output and error streams. It supports renaming the files. It lets you look at those log files as the job is running, so you can see the output right away. And it avoids exhausting memory or exhausting your home directory space if you were to use this option when jobs produce large quantities of logging messages. So the only thing you'd have to worry about there is if you run out of scratch, but the odds are if you run out of scratch, your job's going to fail anyway. So that's kind of a subtle resource, but it's something to think about. Now, here's a Casper example. So here's a Slurm batch job. And in this example, I'm submitting a hypothetical machine learning or AI GPU job on Casper. Things are a little more interesting here. So here I'm reserving a single V100 GPU for the machine learning job. And we've talked about this before, but it's important to note that I'm using the GRes option. There's kind of two ways we've talked about in the past to get GPUs on Casper. One is with this generic resource flag, and the other is with a constraint or -C. But things changed over the summer, and now you need to use this GRes flag, because what that actually does is it reserves the GPU for exclusive use for you and your job. You shouldn't see any other users on that GPU, which is nice if you're running something that's rather heavy. Now for the GP100 jobs, if you were to run on those GPUs, you can use the constraint because those are shared GPUs. They don't get reserved exclusively. Now here we're requesting 4 CPU tasks. I've seen in the literature online that it's pretty common to use 4 to 8 CPU tasks to manage data for a single GPU in a lot of machine learning frameworks. That's certainly worked well for me in the machine learning jobs that I've submitted performance-wise. So here we're requesting 4 tasks to feed data to the GPU work. And this is tailorable based on your workflow, but these machine learning /GPU nodes are really configured. The hardware is configured to do intensive large data processing. So here I'm requesting 40 gigabytes of node memory to buffer data movement to and from the GPU from the CPU. Because remember, the GPU has 32 gigabytes of video memory. So I'm allocating a little bit more on the node because even in these machine learning jobs where you're really hitting the GPU hard, I think people can be surprised how much work the CPU is still doing in the background. What I'll say later in the talk is that you can be conservative initially with these resources. So here I'm asking for 40 gigabytes, which is probably more than I'll use in this job, but then I can query it in the future and lower that requirement if I find that I'm not using that much. And again, the temp space on the node can be small, so we suggest that you use Glade Scratch for your temp files, regardless of which system you're running on. And here's the Slurm equivalent of storing my job output. So here I can use scontrol show job and give it the job ID. And that variable and the PBS job ID variable are defined by the scheduler, so you don't need to define that. And that will include CPU and memory usage output from Slurm. Again, that information is purged very quickly. I've seen it disappear, say, 10 minutes after the job has run, at least in the scontrol command. You can get it in different ways from Slurm. But I like to dump that output since it's so quick to go away and store it in my logs. So for resource allocation and the shell in interactive Slurm jobs, this is one of the more complicated things in terms of being aware of your resources. So we have the script execdav, I'm sure you've probably all used it, and what it does is it simplifies the process of provisioning an interactive session on Casper, which happens behind the scenes in a two-step process. So the base Slurm commands, you run an salloc, and that provisions the resources to a Slurm job. And then you use srun to distribute some portion of those resources to a process. And in this case, we are distributing those provision resources to your shell process, either bash or C shell typically. So execdav combines these two tasks for you and simplifies that. Now, we have to make a choice there. So by default, we distribute all of the memory and the GPUs that you request to the shell, leaving none for other subjobs, or in Slurm calls these job steps. One example of these that's particularly relevant is if you try to run a program within your shell using the srun command. So srun will anytime you run srun, it wants to pull resources from that pool that you provision using salloc. So to get around this, what you can do is you can specify shell resources after a separator, and that is this double dash syntax that we put into execdav. So in this case, in the first example here, I'm distributing all the resources that I requested to the shell, in this case bash, because I'm a bash user. So I asked for 4 CPU tasks, I asked for 10 gigabytes of memory, and I asked for 1 V100 GPU. And all of that is going to get allocated to the shell process. And anything that you run within the shell can use that stuff. But if I try to do an srun within that shell, it's going to look for resources that the shell process isn't using and not be able to find any. So that's a problem if we run another srun command. And I think it'll become clear when I go through some more examples. But a way to get around that is to only distribute a small subset of the resources to the shell process. So here I'm asking for the same resources in my job, but in my shell, I'm only going to use 1 gigabyte of the 10, and I'm not allocating any of the GPUs to the shell. I'm going to reserve those for other srun calls. This can yield some complex interactions. So let's say I wanted to run a Jacobi solver. So this is just a pretty simple grid number cruncher. And I'm going to use MPI, and I'm going to run on GPUs as well using CUDA. So this is an example that NVIDIA provides as part of their MPI GPU example set. So in my first experiment here, I'm going to try requesting 2 tasks and 2 GPUs, and I'm going to allocate all the resources to the interactive bash shell. So here I run my execdav. I'm going to give it 10 minutes, 2 tasks, 10 gigabytes of memory, and 2 V100 GPUs, and it's all going to go to the shell. Now, you can see right here, if I try to then run my Jacobi code, which again uses MPI, using the srun launcher, and here I'm using this -i flag to tell Slurm, I want to find these resources right away, and if I can't find it, just give me an error. Otherwise, Slurm will try to wait for resources to become available, which will never happen because they're always allocated to the shell for the duration of the job. And you can see I get an error right away, and it says unable to create the job step for this job. All the requested nodes are busy. And you might think, well, I'm not really running anything, but I am running that bash shell, and I've allocated all of my resources to it. However, this is an application that I've compiled with OpenMPI. So OpenMPI has its own launcher, MPI run. And if I use MPI run to run the same code instead of the Slurm integrated launcher, it runs, and that's because it's pulling the resources from that bash shell. It's a child process of the bash shell, so it has access to those GPUs and it has access to those tasks. But if you look closely at this, you might think, well, GPU computing is terrible, because here it says if I use one GPU, it takes 6 seconds, and if I use 2 GPUs, it takes 70 seconds for a speed up of 0.09. So that stinks. And the reason for that actually is when we ask for 2 tasks, what Slurm will do is it will give you, it's very likely that it will give you 2 threads on the same physical core. So 2 hyperthreads on the same physical core. That works well for some workflows, like if you're just doing some, simple data processing in a lightweight script, that works fine. If you're doing a Jacobi solver or an intense machine learning algorithm, that's not going to work very well, as you can see here. It's not very efficient. So what we can do instead in the second experiment is I'm going to request 4 tasks. So then I'm going to get 2 physical cores and 2 GPUs. And again, I'm going to allocate all the resources to the interactive bash shell. So here you can see the only thing I've changed is I've made this dash number of tasks 4. So I know that the srun isn't going to work, so forget about that. But now that I have 4 tasks, I can do my MPI run with the Jacobi, and it's still bad. And the reason here is that the way that this Jacobi program was written, again, I didn't write it, but the way it was written is that for every CPU task that you are running, basically it expects 1 CPU task per GPU. And it appears that it determines the number of GPUs based on the number of tasks, not any sort of information coming from, say, the CUDA API. So it now thinks that there's 4 GPUs, and again, my speed up is terrible going from 1 GPU because there's just a ton of resource contention going on here because you're running 4 GPU workloads on 2 GPUs. So what we can do is instead we can say, I'm going to use 2 CPU tasks to drive the application, so I'm going to avoid stacking work on these GPUs. And finally, we're seeing the performance that we would expect. So, we have a performant case on a single GPU, and we have about double the performance actually on 2 GPUs. So this is scaling great now. But you can see how if you don't think about those resource requests carefully and how you run them, your performance can be pretty poor, and you might not know why. At least not without doing some experimentation. Now, there's a third experiment here. So here, in this case, I can request 4 tasks, because we know that's important to avoid the hyperthread on the same physical core situation. And I'm going to request 2 GPUs, but here I'm going to reserve most of the memory and both of the GPUs for subjobs that I run using srun. And here, so this is what this looks like. Again, it's a 10-minute job, 4 tasks. I'm going to ask for 11 gigabytes instead of 10 now of memory because I'm going to reserve 1 gigabyte of that for the shell. And I'm going to ask for the 2 GPUs, but I'm not going to assign those to the bash shell. So here now I can use srun. So now I'm pulling at those resources that I didn't allocate to the shell using srun because they're kind of just in this pool of available resources that Slurm considers. And I'll run my Jacobi code. And here again, we see the same problem in that, that it thinks that there are 4 GPUs when there's only 2. So my performance is poor. Although interestingly, I do get a speed up still. So something slightly different is happening here when I'm using srun. But the absolute performance for both cases is still not where I'd want it to be. This one I included because I think you might look at this as, if you were running this code and think, well, it's working properly in the absence of any contrasting information. But if I subset it to use only 2 CPU tasks, then my performance is much better, even though I'm not super scaling anymore. I'm actually scaling exactly as I would expect, about double performance using double the GPUs. So this is the best case here. Now, if I try to use MPI run in this situation, I haven't allocated any of the GPUs or enough memory to the shell. So basically, I get a segmentation fault because OpenMPI is trying to run CUDA code and it's trying to send GPU instructions to GPUs that it can't find. So again, this is a complicated situation, and it's a bit simpler if you're submitting batch jobs, but I wanted to show you the more complex case. Okay, so that's a bit about scheduling resources. The other side of it is querying past resource usage, and you can do that different ways on each system. So PBS doesn't really have a great internal way of doing this, so we in CISL wrote a utility called QHIST, which you may have run across, and this allows you to query into the PBS historical job database. So you can do things like search for all your jobs over a date range, or you can look back n days from now. By default, that's 1. It'll look back 1 day. You can display the average CPU and memory footprint per node for each job. And you can even do things like filter to only show jobs that return to non-zero status, so you can look for all of your failed jobs in the past 5 days, for example. Here's a example query for my user. So here I'm restricting it to my jobs, otherwise it'll show all of them, and the list gets very long. I'm specifying a period of basically all of October of 2020. I'm sorting this list by memory usage, and I want my my wall time to be shown in units of minutes. So I'm customizing this query quite a bit, and then I'm piping it into head to only show the top 5 results, 6 lines, including the header. But you can see I've got all of these jobs here that ran on 4 nodes. You can see how long they ran for, 7 minutes. But the interesting thing for the resource usage is I can see how much memory these used. And there I can get a sense of what my memory requirement is without having to do any sort of instrumentation within the job. Now this does show you an average. So this is saying I'm using an average of 49.2 gigabytes of memory in each node, basically. So the total memory usage of this job is higher, but that's the average per node. And this is the average CPU utilization per node. And that's not 10% of one CPU, that's 10% of all the CPU resources on the node. So 10% of the 36 cores. Now in Slurm, you can do something similar. Slurm has a built-in command called SAccount. So this is also looking at an accounting database, basically, but it provides a lot of historical job information. So you can view your jobs over a given date range, and you can customize the output fields to show only the information you want. Because I find the default information from SAccount doesn't really give me the information I'd want from a user perspective. And you have to remember that Slurm has this concept of job steps. I've called them sub-jobs occasionally. So resource usage that you find for your job is typically in the step, and it'll be the job ID .0 or .1, .2, .3. So that'll be the syntax for the job steps. And that's what this would look like here. So here I'm using an environment variable that they define, this SAccount _ format, to specify the different fields that I want. And if you look at the manual page, or if you go on the web documentation for Slurm, you can see the different options that you have here. But I like it to show the job ID, my username, the end time for the job, the elapsed time, or the wall time, the number of CPUs and the number of nodes, the memory that I've asked for, so that's this required memory, and the maximum usage for the job, and then give the state of the job, so whether I know whether it's completed or still running, or what have you. And then I run the actual SAccount command, so I filter it again by my username. I specify a start and end time. So here I'm looking for the month of August in 2020. And I like to unify the output so that all of my memory output shows in units of gigabytes, because otherwise it will try to show it in whatever unit it thinks is logical for the amount. But I like it to be uniform. And then I get this output here. So I can see right now I'm showing 2 jobs. And again, we have these job steps. So you can see the requested memory for the overall job, and then you can see the requested memory in this job step. And they can be different. remember this is kind of your pool of all of your resources in the main job, and then the job steps have a subset of the resources, but here all of the resources got allocated to that job step. And the usage actually happens in the job steps. So here are examples that I think are somewhat illustrative. Here I've asked for 40 gigabytes per node, so this is GN per gigabytes per node, and I've used 6.73 gigabytes. So that tells me that my resource request may have been a little high, and if I resubmit this workflow, I might be able to bring it down to 20 gigabytes or even 10 gigabytes if I'm comfortable that this is a fairly steady usage amount. And then my job will likely run sooner. So this is the kind of iteration that we like to see and we think is good stewardship of the resources and also beneficial for you. Here's an inverse example. So here I didn't specify any resource request, and by default I get 1.78 gigabytes per core. And this job step only has one core, so that's my total amount. But I used 3.57 gigabytes, and I'm able to go over what I asked for because of that swap space. So it's nice that my job didn't fail, but my performance was probably pretty bad in that job because I was writing to a solid state disk instead of RAM, and your performance will suffer. So there's other kind of simple ways to look at resource usage on a single node. You can do this at runtime, or you can do it in a batch job. Most people are probably familiar with top, and top is a very powerful command. There's an interactive mode that has tons of options. You could spend a couple days, I think, learning all the different options, but it provides great information. There's also a batch mode that you can run. So if you're not interactively using the node, you can do this -B, give it a count of ones. This will do one sample, show all of the jobs for me. And then I use this -O option to sort it by the memory field, the percent memory column here. I could also sort by the resident memory as well. That would give me a similar sorting. But here I can see my processes that are using the most memory, or I can sort by CPU or timer, whatever I want. And the plus just says to sort in basically the largest amounts on top. So here I'm running that Jacobi solver with 2 CPU tasks, and I'm able to get this information and dump it into a text file, for example, if I wanted, store that information. This doesn't give you any information on GPU utilization, so that's something to be aware of. But there is a command, again, it's a pretty powerful command that NVIDIA provides. It's called NVIDIA-SMI, and you can get information about the GPU specifications for one, and you can get information about your usage. So here I'm using NVIDIA SMI with this PMON option. This is process monitoring, I guess. And again, it's an interactive command, but I can specify a sample count of 1, in which case it'll work in more of a batch mode, so I can dump the output to a file. And what this command shows you is it shows you the GPUs that you have access to. So here I have access to 2 GPUs, the process ID. In this column, it classifies it into either a compute task or a graphics task. This is your multiprocessors. So again, it's kind of analogous to the CPU usage here, %. This is kind of the GPU usage. And then the memory usage on the GPU as well. And that one perhaps is the most useful. Yeah, this one tells you whether you're actually using the GPU in an optimal way, of course. But this one will tell you if you're running short on memory, and clearly this Jacobi solver is not. And one thing that I think is I mean, it's not surprising, but it's kind of neat how you can match up the process IDs between top and NVIDIA SMI, kind of get an idea of how everything is interacting in a simple way. Now, if you want to run those commands interactively, you can. If anybody's not aware of this, you can actually access the nodes that your running jobs are executing on to analyze the resource usage. So for the duration of your job, you do have SSH privileges to access the scheduled compute nodes. And with QStat, you can use the -N option to get node information. SQ provides a node list field by default, so that'll tell you what nodes your job is running on. And once your job has a node and it's running on it, you can simply SSH to it from one of the login nodes. But you should be aware that once the job ends, then your session on the compute node, your SSH session, will also be terminated. So you can get bumped out kind of surprisingly at times. Here's an example. So I have this job that's running. I run a qstat with this -n option, and it's a single node job. I find out that it's running on this node here, R9, I4, and 10. So I can take that, I can SSH from the login node to R9, I4, and 10, and now I have a shell session on that node. And that, you know, I can do this if I'm running a batch job as well. So it's kind of interesting if you're running like CSM or WARF or something like that, or MPAS, you can go and SSH onto one of the nodes and run top, for example, and see what the processes are doing. One example where this would be nice is if you have a program that you think may have stopped executing for some reason, like you're not getting log output anymore. You can SSH onto the node and see if those tasks are actually still running or if they're in like a zombie state or something like that. So that's a useful functionality. Now there's more complicated ways to monitor your resource usage, and these are useful if you're running an MPI job, for example, across multiple nodes, or like a Dask workflow or something like that that's farming tasks out to different workflows, or different nodes, sorry. So we provide a utility, this one called peak mem usage, and that one will provide the maximum memory usage for each task in a program, and that's on all the nodes. This will give you the node memory only, so it doesn't query the GPU memory. So that's useful for more traditional jobs. And the other thing to note is that this will only give you output if your job completes successfully. So if you run out of memory, you're not going to get any output. NVIDIA provides a program called NVProf. This is nice. It profiles many aspects of the GPU performance, and it stores those profiles for you to analyze in subsequent analyses. This is what we currently have available on Casper. And NVIDIA is in the process of replacing, deprecating NVProf and replacing it with this nSight program. So as we move forward, that will kind of take the place of it. But in either case, you can get a lot of information about how your GPUs are getting utilized by your GT program. And then if you want to kind of extensively profile the performance of a complex code that really uses the CPU and the GPU, or just the CPU, you can run the map program that ARM provides. We have licenses for that on Cheyenne. Going in detail on how to use that is kind of outside of the scope of this, but we have documentation on the web on how to get started. And ARM has a pretty extensive manual for the map program, but it's a powerful profiler. Now, of course, with any of these methods, you are going to have some overhead in terms of the memory usage, and also a bit of a slowdown because it takes CPU cycles to profile what's going on. So that's something to be aware of. Whereas just SSHing into a node and running top or NVIDIA SMI, that's very lightweight, almost no impact to the program. Okay, so this is how you can query information about the resource usage. Another interesting thing would be, or a useful thing would be recognizing resource-related job failures. So sometimes you'll see some clues in the job logs that can motivate some more investigation. One example that we see fairly often, if you get this error, oftentimes it'll get reported by MPT on Cheyenne, the MPI library, but if you see something that says SIGBus, this is a bus error, it's a memory error, basically a memory access error, and most often it indicates that you've exhausted the available memory, the available RAM on the node. And you just need to allocate more memory to your job, either by using more nodes or on Casper by doing a large memory request. You could, in theory, get a bus error because there's actually a hardware issue, but that's rare. It's typically the configuration of the job. This is another thing you might see. It's not a very verbose message, but you might see something like killed MPI run or something like that. That indicates, and this would be in the job log, not in the application log, but that indicates the job was killed by some external process or watchdog. If the wall time limit was reached, then it may just be that it was killed by the scheduler because you ran out of wall time. But if that wasn't the case, if this happened like halfway into your wall time, then it's probably an out-of-memory failure again, because we do have some watchdog tasks that try to kill processes when they've reached the memory limit before they've kind of reached with a tiny bit of buffer, and that prevents the nodes from crashing, and in which case your job's going to fail anyway. So that's kind of a cleaner exit from an out-of-memory condition. Again, another memory error that you'd see on the GPU side, if you see this CUDA error out of memory, that means that you've run out of GPU memory. And you may have plenty of memory on the node, but you have exhausted, say on the V100s, you've exhausted the 32 gigabytes of video RAM. So those are the most often cases for job failure, our GPU, our memory, out-of-memory conditions. If the job fails with no logs, then you may have run out of the temp space, or you may have hit your quota on Glade. Okay, so common job resource pitfalls. You may request too little memory on Casper, in which case some of the data, again, destined for RAM will end up in swap space, and that'll impact your performance pretty significantly, especially if you have a workflow that's very data heavy. If you request too much memory on Casper, this is better, I suppose, but you will likely have a longer queue wait time, and you'll also waste node resources, because what Slurm does is like if I ask for 100 gigabytes of memory, it's allocating that memory to my job, and nobody else can use it. And that's nice, but what we sometimes see is we see jobs that ask for like 500 gigabytes of memory and then use 10 gigabytes. And we'll usually contact you in those cases, because it's problematic it's a waste of the resources, and it also limits the number of jobs that can be running on Casper at any particular time. You can request multiple nodes, but the application doesn't support MPI or some other distribution method like Dask, in which case, again, you're just wasting resources because there's no means to split your workflow across those nodes. And this can be easy to miss, it seems, using GPU frameworks, because those frameworks tend to just try to be smart about saying like, okay, well, I have access to these resources, I'm going to use them. I don't see any MPI integration, so I'm not going to look anywhere else though, because I can't. So you may end up running on one, you might run your TensorFlow workflow on one node, even though you've requested 4 of them with different GPUs. And it might run slow, as you might expect, but those can be hard to notice sometimes. And then just some general tips for scheduling. So I'd say use the fewest resources required to safely run your application, and that'll optimize your core hour usage and your queue wait times. Only restrict the job to specific node types if necessary for the job execution. And that goes into those things like on Casper, I can request a certain CPU type, or I can request, that there be a GPU on the node or something. Only request that stuff if it's necessary for your job, because otherwise then you're limiting the pool of nodes that your job can run on, which will make it take longer to schedule. And very important, and this is kind of why I showed you all those different simple ways to get information about what resources are getting used, verify that you are using what you think you're using, because otherwise it's just a waste of compute time on that machine. So if you're running a job configuration for the first time, like let's say I have this workflow or I have this application or a machine learning task or something like that, and I've never run it before, think conservatively about your resource requests, because you don't want the job to fail because you run out of memory, or you run out of, you don't have enough CPUs or something like that. So be a little conservative the first time you run it. But then, again, verify. Check what your job actually used. And if it's substantially lower than what you estimated, then you can lower your resource requests and get more jobs through the queue. You don't want to lower it right to the edge, because there can be a little bit of up and down bounce in what amount of memory it'll use based on the data that's going in and out. But if you leave, say, a 10 to 20% buffer, that can oftentimes be sufficient to make sure that you have enough resources to run your job. So that's all I have. Thank you for your attention and for joining us. I know we're going to take questions in the chat if you have them, and I can answer those in the time we have remaining. But I just want to say, if you want to get help from us on any of these things, you can go to our Getting Help website there. Unfortunately, we can't do walk-ins until the pandemic is over, but that'll be the place to go when we eventually do open back up. You can go to that website there, the support.ucar.edu, to submit tickets. And during business hours, you can call that phone number and talk to us if you have any questions. And I also encourage questions from today, or if you have any feedback, or things that I didn't talk about that you'd like to see in the future, you can send me an email directly and I'd be happy to take that feedback. So again, thank you, and we'll open it up to questions. And I think BJ or Mick, I think you were going to read those out. I can bring the chat up too.
Yeah, there haven't been any questions yet, Brian.
Oh, okay. Well, it was too clear.
Yeah, super job.
Well, I'll hang around for, about 5 minutes in case anything comes up, if you're typing out or thinking. And again, of course, if a question comes to mind later, feel free to send either our help desk or send me an email. I'd be happy to look into it with you. Oh, and yeah, BJ put this in the chat, but this presentation was recorded, and we'll make the recording and the slides available as usual on our library page. So, if you want to reference this in the future, it'll be there.
Here's one, Brian, from Johnson. It says in your slides, it seems that you could type execdev in the Cheyenne login node, but enter a Casper compute node later. I guess there's just looking for clarification if that was understood correctly.
Yeah, so if I understand the question correctly, basically when you run execdev on a Cheyenne login node, it's going to provide you with an interactive session inside of a Slurm job on Casper. So you already have an interactive shell session already there. But if let's say I wanted to open up a separate terminal window or a separate screen in like Screen or Tmux or something like that, and have a second terminal session running in that same job, I could still SSH into that job that I started using execdev. So that SSHing in, I think, is often useful for batch jobs where you don't have a shell by default, but you can do it for interactive jobs as well. And let me know if that didn't answer the question, but hopefully I got at what you were asking.
Okay. And then from Rachel, where is the library page?
So that is, you can get to it on our user support page. Let's see if we try to navigate there now. This would be a better question for BJ. I don't know if he's muted.
I was muted, Brian. Yeah, if you go up to the user support tab at the top, you'll see training. And when this video and slides are published in that course library, we will be notifying everyone who registered and sending them a link to that, the exact page. But that's where you can find other resources too, if you could just click on go to course library.
Okay. Thanks, BJ.
Sure.
And here's a good question from Tracy. When first running an application, is there a best approach to determining how many nodes or CPUs to use, or is it just trial and error?
Yeah, that's a tricky one. I mean, that really comes down to domain knowledge, I think. You know, if I'm running a model, for example, then basing it off of tutorials that you can find online, or you know, if you can find a similar problem size, then that's something you could base it on. You know, if you're running something like CESM where you have these defined cases, then oftentimes it's a little bit easier until, at least until you want to modify the case or the configuration. But it does come down to a bit of trial and error, unfortunately. And I think that's just something that you get more used to the more you run it. But I would say, you know, if you're running something like a machine learning workflow or DAST or even a CFD model, basing it off of tutorials and doing a little bit of a quick search on the internet can often give you information, or asking colleagues if they've run it before. It's really hard to intuit that knowledge from, you know, from nothing. I mean, if you have some sense of what the application is, like I'm running like an LES code across a domain at very high resolution, then I know I'm probably going to need more than a couple nodes, but exactly how many can be tricky, and exactly how much memory can be tricky too. So that's why verifying is so important.
No new questions yet. Oh, here's one from Keith. I frequently run jobs in the share queue, single point CESM simulations. Sometimes these jobs seem to just disappear and I can't find any information about why they might have crashed. I can run the same exact job a bit later and it runs to completion. Any hints or ideas?
Yeah, so you know, it's a bit more complicated in the share queue, because in the share queue you are a bit at the mercy of having good compatriots on the same node. You know, obviously, if the node were to crash, which again I emphasize is rare, then you might not see any output. You can get a sense of whether that happened by if you go back to that same node, you can run the uptime command and see if the node's been online for a while. But the more likely scenario, again, you know, check to see if you're making sure that your logs are getting written to a space that you know, permanent storage, or not permanent, but actual disk storage, like somewhere on Glade. That should at least make sure that you get logs. You can run that QHIST command to get a exit code, and the exit code can sometimes be illustrative. Can at least tell you if it was killed by an external process or if it failed for some reason of its own. And you know, decoding those exit codes can be a little tricky, but you can find resources online, or you can contact us for help on that. Sometimes I find that the application logs itself, so this would be like logs that CESM writes, might have information stored in one of those logs. You know, CESM has quite a few runtime logs, so finding out exactly which one has it can be tricky. But you know, and also, again, if you run QHIST and look at your resource usage, and if you see that it's close to, like, let's say the memory use was close to what you asked for, then you know, that might be something to consider. I guess on Cheyenne, close to what the node would allow. And again, on the share queue, that's tricky because that isn't locked down to any particular user. So on the share queue, you're kind of at the mercy of how much memory other people are using as well. Now that will change at some point in the future. At some point, we're going to upgrade PBS to a version that allows you to reserve a block of memory and nobody else can use that, just like it works on Casper, but we're not there yet. So, and at the end of the day, if none of those solutions help, then I would suggest sending us a ticket with some job IDs, and we can try to dig in further and look at the system logs as well. All right, so I think we're at our end of our time window here. So yeah, I think we'll end the session now. Thanks again for attending and for those good questions. And again, if any others come up, feel free to contact me or contact the consulting group. Hope you have a good day.
Thanks, Brian.